everyone. Today we're going to be talking about photon-electron interactions. We're going to get through photon interactions. We're not going to get to electrons in this recorded lecture. My name is Scott Hadley. I'm a faculty member at University of Michigan Radiation Oncology. If you see me in the clinic, be sure and stop me and say hi, introduce yourself. So in this lecture, we're going to talk about interactions of electromagnetic radiation with matter. In subsequent recordings, we're going to cover particulate matter, radiation, interactions, characteristic of photon beams, quantification and measurement of dose, including SI units. So some history of X-rays. X-rays were discovered by Wilhelm Röntgen in 1895 while studying the properties of cathode rays or electron beams. We're still using electron beams today to make X-rays. And he discovered this by applying high voltage across an evacuated glass tube. So he had a glass tube, he had an electrode on one side and high voltage, and these electrons cross the gas tube. They hit the other side of the glass and produce something that was a much more penetrating beam. And because they didn't know what this beam was, the nature of it was unknown and it seemed very new, Röntgen called these new form of radiation the X-rays, right? And a lot of times in physics and math, we use X to designate the unknown, much like Malcolm X, when considering his heritage, he used the X to designate it as unknown because he felt his heritage was lost. So X is like the mystery variable in science and sometimes in history. But what he learned was these things were new, and he learned that unlike anything else he had discovered before or anyone else, the X-rays traveled long distances, greater than 2 meters. We now know that X-rays can travel across the galaxy from one galaxy to another. X-rays go in a straight line from their source, so they start at a source, they move across from one place to another in a straight line. They don't bend or deviate until they interact with something. Their intensity reduces as they get further from the source, so much like any light source, like a flashlight or anything else you have, starts at a particular point and then those X-rays start to spread out as they get further away, known as the inverse square law. And also they discovered that different materials reduced the X-rays by different amounts. So Röntgen, working in his lab, he could put paper, he could put different types of metal or wood or things like that between the cathode ray tube and his detector and find out that all of these things attenuated the X-ray beam by different amounts. So there was some sort of interaction that differed based on different materials. And in all of his studies they found out X-rays are unaffected by magnetic fields. They cross right through magnetic fields as if the magnetic field wasn't there. This was different than their electron beams. Electron beams are moved by a magnetic field. The radiation can penetrate opaque substances. So unlike visible light, if you put like a piece of tin in front of it and block that light 100%, the X-rays could penetrate that. So it was different than visible light. It got attenuated in different mediums. So the attenuator depended on the density and the Z of the material. So the atomic number and how dense the material was. So when they went from low Z materials like paper or wood or human tissue up into things like copper or tin or lead, those metals with higher Z attenuated more. The X-rays darkened photographic film, so when the X-rays interacted with the photographic film, which was the easiest particle detector they had at the time, they could see that something was going on and changing the color of the film. They also realized that it was ionizing gas. And as a result of all of this, Röntgen was awarded the first Nobel Prize in Physics in 1901. So what are X-rays? X-rays are electromagnetic radiation, and you can see this is the scale you're probably familiar with, electromagnetic radiation along this line, and we can see the visible light spectrum is in here. And one thing I like to impress upon is going from like radio waves, infrared, visible light, ultraviolet, X-rays to gamma rays. These are all the same type of particle that we have in physics. It's just different wavelengths and different energies. They move at the speed of light. They go in a perfectly straight line forever until they interact with matter, and then a lot of times the X-rays are either scattered or absorbed, but they tend to disappear from our universe. Another thing about X-rays is we label them differently based on where they come from. So A lot of times X-rays are what we call it when the X-rays are generated by a device like an X-ray machine or a LINAC. Gamma rays are what we call them when they come from a nuclear decay or something like that. And off the scale here, right, which would be right here, we have cosmic rays. Cosmic rays are what's coming from some other part of our galaxy, or maybe even a different galaxy, these super highly energetic electromagnetic radiation. But ultimately, it's all the same particle. So an important thing about X-rays, before we get into the interaction, you have to remember your Bohr model of the atom, or the structure of the atom, where you have the nucleus in the middle. It's got a certain number of protons in it, which is its atomic number, and then the electrons are bound to it in different shells. We have K, L, M, N, and O shells, and the number of electrons held in those shells increases as you go up through more and more. Each of the shells have a negative binding energy, and the binding energy is highest when you're closest to it. So the K shell down here is closest to the nucleus. It has the highest binding energy. In this example here, O has the weakest, at least diagrammed here. There's no electrons in O. And the binding energy is less than the K binding energy is less than the O binding energy. And we're just calling this negative energy. So the K has a negative energy, and if we want to get the electron in the K shell off, we have to add a bunch of energy to it to rip it away from that nucleus. And the binding energy, that's an important concept for us in medical physics. It's the energy required to remove an electron completely from an atom. So here we have a proton and an electron. The binding energy is the energy need to separate these two, right? One's positive, one's negative. They tend to stick together, or really the electron orbits around the proton. And if we want to get those two apart, we got to rip them apart, and we're going to do that using X-rays. The binding energy goes up with the more protons and higher Z. So if we have 2 protons, we're going to have 4 times the binding energy to remove. The binding energy also goes down as the shell increases. So down here we have 3 protons, the K shell is filled, this electron in the L shell has a lower binding energy, and it takes less energy to pull that electron away from that nucleus. So just keep that in mind when we talk about X-ray interactions. Energies of the X-ray, so the energy of an X-ray, E, is equal to Planck's constant, H, times the frequency of the X-ray. And every X-ray has this frequency on the electromagnetic spectrum. Another equivalence to know is that the speed of light is equal to the frequency multiplied by the wavelength. And here we have the frequency is measured in once per second, or hertz. The wavelength, we typically use meters, which is the SI unit. The speed of light is 3 times 10 to the 8 meters per second squared. And the energy of the X-ray, typically we would use joules because that's the SI unit, so we designate it as J. But practically what we use in medical physics is the electron volt. And so I'm going to explain what an electron volt is quickly. And Planck's constant, that's 4.1 times 10 to the minus 15 electron volt seconds. You could also use joule seconds for this. And that's just a constant of the universe that you just have to know what it is. So what's an electron volt, right? Because I'm going to talk a lot about X-ray energy, so I have to tell you what an electron volt is. You can think of this, I'm going to use an electron to describe what an electron volt is, and it's the energy gained by an electron when it falls through 1 volt potential. So in this diagram right here, I have a voltage source. I set the voltage source to 1 volt, and then I take an electron up here at the positive pole of this capacitor, and I let it get attracted, or I should say the negative side of it, and it gets pushed or pulled to the positive side of it. And because the voltage from here to here is 1 volt, and the electron starts here with no velocity and travels to this side with 1 volt of pull, we call that 1 electron volt. And you can imagine maybe like Röntgen in his lab is cranking up his voltage supply from 1 volt to 50 and 100 and maybe 1,000 volts, and accelerating electrons from one side to the other in a vacuum. We don't typically use 1 volt for anything. 1 electron volt is not a lot for us in medical physics. We're usually up here in the millions of electron volts. So let's say like we have this super high power voltage source. We have 1 million volts from this side to this side, and we take an electron, which is initially not moving at all, and we push it and or pull it from one side to the other. We get a 1 MeV energy electron going from one side to the other. So this is going to fall from one side to the other. It's going to speed up. It's going to get to a maximum velocity by the time it gets there. And when it gets there, it will have 1 million electron volts worth of energy. And we use the same concept for X-rays. So a lot of times with the X-rays, we'll just tell you how many electron volts or kilo or mega electron volts it has. So just jumping back to energy now that we know what an electron volt is. The energy of the X-ray is Planck's constant times the frequency. If I ask you to do this calculation, I'll have to tell you what the frequency is. And in this one, the frequency is 1 times 10 to the 17 electromagnetic cycles per second. Planck's constant is 4.1 times 10 to the minus 15 electron volts per second. And when I multiply this out, I get 4.1 electron volts per second times 10 to the 17s per second. And the energy of an electron with this frequency is 4.1 times 10 to the 2 electron volts. And that's kind of in a range of what's typically used in our field for imaging or something like that, or actually superficial X-ray treatments. This energy is really important. Like a lot of times all throughout in the clinic and in doing imaging and things like that, we're always talking about what energy electron we're using for therapy, what our tube voltage is set to. This determines what our X-ray energy is. And so the X-ray interactions change a lot with different X-ray energies as we scale from, let's say, 100 electron volts up to 1 million or 6 million electron volts. The interactions change drastically, which is important for us. And different radiotherapy treatments use different X-ray energies. And I should add in here, different imaging techniques use different tube voltages and different X-ray energies. So the energy is always very important to keep in mind. So we're going to talk about interactions of electromagnetic radiation with matter. We're going to talk about coherent scattering, photoelectric effect, Compton scattering, pair production, and also photodisintegration. These interactions are more prevalent with increasing X-ray energies. So as we ramp up the energy of our X-ray, we're going to scale from coherent being most likely to photoelectric effect, Compton, pair production, and photodisintegration. So we're going to talk about them in that order. So coherent scattering, also called Rayleigh scattering, typically happens with low energy X-rays. When this happens, the X-ray interacts with the entire atom or all of the electrons in the atom. And you can see here in this diagram I have an X-ray coming in with a certain wavelength, kind of interacts with its entire atom, and then we have this X-ray going out in a different direction. And the way I drew it here, these two have the exact same wavelength, so they have the exact same energy. So the X-ray leaves with the exact same energy but in a different direction. These are rare interactions. About 5% of X-rays do this interaction when we're doing imaging like CT scanning or KV imaging or something like that. I guess 5% isn't that rare, but it's not too common. And in this diagram, I didn't diagram it here perfectly, but there's no dose contributed to the patient when Rayleigh scattering happens, right? Conservation of energy. If this X-ray comes in with the energy and leaves with that exact same energy, no energy was deposited in the patient. Photoelectric effect is the next one. Basically, I described this in 3 separate steps. So the X-ray comes in with an energy greater than the binding energy of the electron that it interacts with. And in this diagram, we can see this X-ray comes in, it chooses to or happens to hit this K-shell electron and interacts with it. And this electron completely absorbs this X-ray, right? This little explosion happens, this X-ray completely absorbs, disappears from our universe, and all of that energy goes into the electron that was bound to the atom. And because the energy is greater than the binding energy of that electron, this electron is ejected from that atom and completely removed from it. If the X-ray has less than the binding energy of the electron, then nothing happens at all. Or it may be that it does Rayleigh scattering or something like that. So the first step of photoelectric effect is X-ray comes in, gets completely absorbed by an electron that's bound to the atom, and that electron gets ejected and creates an ionization event. And then step two, it's kind of like the nothing step. There's a hole here, right? So this electron's gone. It went away. And nature loves to fill this, so we have to fill that hole in. So what happens is the hole is filled. These atoms don't like missing electrons. They're going to pull electrons towards them until it gets all of the lower shells filled. So what happens is that it will fill this shell with an electron that's in one of the higher bound shells, right? So it may choose for the electron that's right here to fall into this. It's going from a higher energy state to a lower energy state. It has to give off energy to do that. And the way it gives off that energy is by making an X-ray. Or this M shell electron right here can jump all the way down into the K shell. Doesn't happen as often, and it gives off another X-ray when it does that. And you can also get these cascade effects. So if this L shell electron jumps down to the K shell, well, then the L shell is empty. Then we need an M shell electron to jump down to the L shell, and you'll get two X-rays. You'll get a K and an L X-ray coming off of it. So the X-rays move from electrons moving from higher shell to lower shells. The X-ray has the energy that's the difference in the binding energy. So the difference in the binding energy between L and K is going to be the energy of that X-ray, or from M to L, it's going to give off. They're labeled by what shell the electron goes to, right? So you can see here, this X-ray came off. I'm calling it a K alpha. It's K alpha because it came from, or it's alpha because it came from the L shell, which is the very first shell above it, and it's called a K electron because it's going into the K shell. So this is a K alpha. In this example up here, this M shell electron is called a K X-ray because it's jumping down to the K shell, and it's called beta because it's two levels above it. It's the alpha beta shell jumping down in here. And then look at this X-ray coming off. When this X-ray comes off, this one's called the L shell electron, and it's called alpha because it comes from the M shell, which is just one above it. And so this is one of the ways that scientists use to characterize what atoms are like inside a sample that they don't know. They can take a sample, they can bombard it with some X-rays, and then they look at what characteristic X-rays come off, and because all these binding energies are all kind of unique for all the different atoms, they can measure the electron energy and then figure out what something's made out of. The next interaction we're going to talk about is Compton scattering. Incident photon interacts with a loosely bound atomic electron. So this one's a little different in that two things are different compared to photoelectric effect. One, it's interacting with one of these weakly bound electrons, and two, instead of just giving off an X-ray, it's going to give off an X-ray and a resulting, or I should say give off an electron and a resulting X-ray. So it's coming, results in one new X-ray and one electron coming from the atom. The new X-ray has less energy than the old one, so the old one comes in with higher energy. Some of that energy is converted into kicking out this electron, and some of it is converted into making a new X-ray with lower energy. And we always have to conserve energy in there when we're having any type of interaction in physics. And one thing I didn't mention in the previous slides is that when these electrons get kicked out of these atoms, they're basically contributing dose, which I'm going to get into the next lecture. So when this electron streams away, it ionizes other atoms, right? You can imagine this atom's not so big. It's ionizing as it goes away, and that ionization is dose. Incident photons can be scattered up to 180 degrees with respect to the original direction. And if the photon is scattered back in the direction of the initial approach, or 180 degrees backwards, it's called a backscattered X-ray. And this backscatter is one of the ways that dose gets backwards in our patient. The angle of deflection decreases, the energy retained by the scattered photon increases. So you can imagine if this X-ray comes in and it scatters at nearly the same direction that it came in at, that's minimal energy transfer to the electron, whereas if it scatters backwards completely, that's maximum energy transfer to the electron. Compton interactions happen most commonly with the outer shell electrons, the one on the outside. They have the lowest binding energy. And the Compton electron is scattered in a direction of plus minus 90 degrees with respect to the incident photon. So this electron that's bounced out, it can only go this direction to this direction in this whole area. It's not able to bounce backwards, right? You can imagine if it's like a pool ball, if you hit this electron with this X-ray, it can only go forward or glance off of it and go sideways. It's the only direction it can go. It can't go backwards at all. And a lot of times the binding energy of this outer shell electron is so small, it's almost always negligible. So the energy transfer to the electron is negligible, so we usually forget about this, and we know that the energy of the outgoing electron is just the incident energy of the X-ray, subtracting off the energy of the X-ray that's produced in exiting. The energy is transferred to the electron is maximized when the photon's backscattered. So when the X-ray comes in and this resulting X-ray bounces completely backwards, we get the most energy transfer to the electron. One of my favorite electron interactions, I'm a medical physicist, I'm allowed to have a favorite, is electron-positron pair production by X-ray interaction. And this one's really fun, because what happens is you'll have this really high energy X-ray come in here. It has a threshold again. There's a threshold energy for this one. And this X-ray will come in and it'll kind of interact with the nucleus as a whole. This X-ray disappears. It gets completely absorbed by this nucleus. This nucleus has to do something with that energy. And as a result, it'll produce an electron-positron pair. So it'll produce one electron here, one positron right here. The atomic number of the atom does not change, right? Because if I take this -1 and +1, that's charge neutral on this interaction. So this atom doesn't change, but it does produce this electron-positron pair. And the threshold is that, you know, this is E equals mc squared, right? Einstein told us that energy and matter are just different forms of each other. You're just converting one from the other. So what we're doing is we're taking this X-ray, which is greater than 2 times the rest mass of the electron-positron pair. It's getting converted into matter. Here the electron negatively charged, the positron positively charged, and any extra energy is going into pushing these two away from the nucleus. And these electrons slow down. So this electron will zoom away from the nucleus. It's going to contribute dose as it slows down and stops inside the patient. The positron is going to do the same thing. So the positron will exit this nucleus. It'll travel through our patient for, you know, a millimeter or something like that. It's going to contribute dose as it goes along, because as far as nature is concerned, this is almost identical to an electron. It's just positively charged. But positron is antimatter, right? And this is why this interaction is so much fun. This positron is antimatter. It's not supposed to exist in our universe. We're a matter universe and not an antimatter universe. So at some point in time, this antimatter has to go away. It's not allowed to be here. So eventually, it'll find an electron buddy. These two will team up with each other. They'll stick to one another when this positron's moving slowly enough, and basically explode into an electron pair And here it's diagrammed as half the rest mass going off in one X-ray that has an energy of 0.511 mega electron volts, and the other half going here, another 0.0511 mega electron volt X-ray. And for the most part, they'll go back to back, not always, usually 180 degrees. And that's what happens to this positron. And then these two X-rays, these can go then do X-ray interactions somewhere else inside the patient's body, like a 0.511 MeV X-ray is pretty attenuating, so these X-rays will go somewhere else and contribute dose somewhere else inside our patient, which is kind of how one of the ways that X-ray energy leaks outside of our X-ray beams. So if the incoming energy is greater than 1.02 mega electron volts, which is 2 times the rest mass of the electron, positron, the X-ray energy is distributed between the positron and electron. It doesn't have to be equally shared. The only thing you have to do is conserve the total energy and the total momentum of this whole system. Pair production is not relevant for imaging like diagnostic radiology, CT, or KV imaging, or things like that. It's really only of interest when you're using high energy photon beams greater than 10 MeV. So if we're using a beam this high, you can't get pair production happening. And the probability of pair production is kind of proportional to the Z of the material and the energy of the X-ray that's coming in. One cool thing about this, if you're familiar with positron emission tomography, some people have done PET imaging using a high energy mega voltage therapy beam. It's not easy to do, but it's a way that you can actually do positron imaging on where your mega electron volt X-ray beam is contributing dose inside the patient. There are papers out there. It's not very practical, but it is possible. Our last interaction we're going to talk about, photodisintegration. Photodisintegration is another interaction where the X-ray comes in. You can see this X-ray is higher energy than any previous X-ray we talked about. It hits the nucleus, and instead of doing something like pair production, it hits one of these neutrons, which are beige because they're neutral, and it ejects this neutron straight out of the nucleus of the atom. This only happens when the energy is really high. So if this X-ray energy is greater than 10 MeV, it's possible for this photon or X-ray to interact, get totally absorbed by the nucleus, and have one or more neutrons come out. In most cases, this results in emission of a neutron, changing the atomic number of the atom here, but not the, I should say the atomic, it changes the atomic mass of the atom, but not the atomic number. We have this designation, so we have something we call slow thermal neutrons. So when the energy of this neutron coming out is less than 0.5 electron volts, pretty low compared to what we've talked to quite a bit. Those are slow thermal neutrons, and some of the fast neutrons are greater than 0.05 eV, and that's like a physics distinction we use. This photodisintegration is pretty important. You have to take special precautions for therapy rooms operating at greater than 10 MeV to stop neutrons that are produced. And sometimes you have these mazes. You know how sometimes our X-ray rooms have like a long maze and a complete 180-degree turn in them. It's to try to help keep the neutrons inside the room. And then along the walls or maybe at the door, they have these special shielding. So they basically have paraffin, which is a wax material that's high concentration of hydrogen. And remember, hydrogens are roughly the same atomic mass as neutrons. So when they hit each other, it's like billiard balls bouncing off of each other. So a neutron will come in and these two will scatter. They'll share their energy and go off in different directions and do that again and again and again. And it kind of moderates and slows down these neutrons quite a bit. But as the neutrons slow down, eventually they're going to create X-rays and photons, which are then attenuated by lead. So some of these rooms have a special door that's like a layer of paraffin wax, lead, paraffin, lead, paraffin, lead, kind of like a layer cake of all these to slow down the neutrons and attenuate the X-rays that are created. And so In some therapy rooms with really high energy, you'll see they have like an enormous door, like a really huge, big, thick, heavy door. It's because it's all these layers of paraffin and lead. It's like a specially designed door. Um, the other thing that happens with photodisintegration is um, all these neutrons created inside the therapy beam, they're really bad for electronic equipment. So you really need some electronic equipment that's hardened. You may see, I don't have a picture of it here in this slide, but you may see like the video cameras inside the room start getting that speckly appearance in them. It's because the neutrons hit the actual video sensor of that camera and help destroy some of it. This is also why patients with pacemakers, we say that they should use energies of 10 MV or less, which in our department basically means they have to be 6 MV X-ray treatments, to keep these neutrons from being produced and potentially damaging a patient's pacemaker that they have for their cardiac symptoms. So for the most part, we try to avoid higher energy X-ray beams and just stick to the lower energy ones. So this is one of my favorite graphs in medical physics. It kind of puts all of the X-ray interactions together because it's important to remember I basically went through 5 different X-ray interactions. I'm going to tell you here in this slide 3 of them are most important: photoelectric effect, Compton effect, and pair production. And they're all happening simultaneously at the same time. So in this graph you can see we have atomic number of absorber inside our patients, and for the most part, most of our patients have atomic numbers of tissues down in this region. This is photon energy in mega electron volts. So when we're doing imaging, we're using energies in here. We're doing X-ray interactions down in this area. When we're doing therapy and treatment, we're treating up in this area, about 1 MeV X-rays that are used. Brachytherapy is somewhere in between here. And you can see that if we're all the way down here at 0.1 MeV, which is like maybe an imaging thing, certainly we're basically dominated by mostly Compton effect, and we get a little bit of photoelectric. And then as we scale up the energy into more of a therapy beam, it's mostly Compton effect going on. We have to get to really high energies to do pair production. But even when we're at pair production, we're still doing a little bit of Compton, a little bit of pair production. When we're at low energies, we're doing some Compton, some photoelectric effect, a little bit of coherent scattering, not all that much. But every time an X-ray beam starts passing through the patient, at any given time, one of those X-rays could do photoelectric, it could do Compton, or it could do pair production or photodisintegration or something like that. It's really kind of random which one it does. And this graph kind of helps describe which interaction is most dominant at different X-ray energies.